Start off very much like Mars Direct. You take your liquid hydrogen and carbon dioxide from the atmosphere, you run them through a body-A reactor, 4-to-1 ratio, you produce heat. That produces heat so you can run it through a water-gas shift, reverse water-gas shift process, in which you take the carbon dioxide and only 1 unit of hydrogen, and what you get out of that then is some waste carbon monoxide and excess oxygen so that you can get an optimal ratio of propellants of 3.5 to 1. Once you've exhausted the vast majority of your hydrogen, you take just a little bit of the leftovers, you set it aside in a separate tank. 2 or 3 kilograms will be enough. And then you take that hydrogen, you mix it with carbon dioxide through the reverse water gas shift process, and now you're using your solar panels also to produce heat, because you no longer have the Sabatier process there to produce all of it for you. So it's slightly slower than the Sabatier process directly. But when you're done with that, you come out with liquid carbon monoxide and liquid oxygen in a 1 to 1/2 molar ratio. The propellant projection requirements are right there. By the time you work it all through, you figure it'll take somewhat less than a year to produce all the propellants on the surface of Mars using the systems described. Now, that's the MAV. What does your person land in? Well, your person essentially lands in a box. A very short box. The drawing showed almost looking like a coffin, but it's actually bent a little bit to try and fit inside the volume space. And when you get down to the surface, you unfold it so that you can sit up in it, so you can drive around in it. The rover, again, the basic unit is 300 kilograms. The capsule on top is 425 kilograms. That sounds very light, but I'll explain that in a minute. And then, of course, your consumables and the astronaut. A company called Retro Aerospace, headed by George Herbert, has been working on a project called Project 248. It's how do you build a capsule to send 2 people to the International Space Station, keep them alive for 4 days, with a total mass of 800 or 900 kilograms. Well, if it can get you back to Earth, that means it has a heat shield. If it can dock with a space station, it means it has a reaction control system. And if you're having 2 astronauts, well, that's twice as much space that you need. So we can remove a lot of that mass by simplifying the design. And then finally, when you're in space, how do you stop at Mars? Mars Direct says, well, use aero capture. We've never done aero capture. It's not impossible, but it's hard to do, specifically because of the unknowns and the density of the Martian atmospheres. It changes with the seasons and with the day. So if you hit it wrong, you wind up burning up, and if you hit it too shallow, you just skim right past it. So the answer I came up with is, well, let's do it propulsively. It's not a whole lot of delta V. It's significant, but it's possible. So I came up with this idea for a propulsion module that weighs about 4 tons. It has a little system for docking attached to it. Its dry mass is 420, so that's a mass ratio of 10 to 1, which is a good thing we're using methane instead of hydrogen, because the extra density really helps with that. And it has a specific impulse of 360 seconds. So how does the actual mission altogether work out? Well, year 1, you could do this all in the same year if you want to wait for the propellant while you're sitting in orbit. But for this, we say year 1, a single Delta IV Heavy lifts 2 of these aeroshells containing 2 of those ascent units in it. You go straight to Mars. They do a direct blasting entry, just like Mars Science Laboratory or the exploration rovers. 2 years later, a SpaceX Falcon 9 Heavy with a Centaur in it lifts 2 of these propulsion stages to Mars, trans-Mars trajectory. Another Delta IV directly lifts the manned landing vehicle and a propulsion unit towards Mars. And then another Falcon 9 Heavy lifts the manned space capsule and another propulsion unit for braking. What does it look like? Well, for starters, you land your 2 vehicles on the surface of Mars. They deploy. The landing accuracy of the science laboratory system is about 20 kilometers long by 10 kilometers wide. It can land something somewhere inside of an oval that size. So you land the 2 units. They drive for a few days until they meet up pretty close to each other. And then they deploy their solar panels and they start making their propellant. 2 years later, The Falcon 9 sends these two modules towards Mars. The first propulsion stage is used simply to break the second propulsion stage into a low Martian orbit, where it will be later used. Then in high Martian orbit, the Delta has launched the manned capsule in the propulsion stage, which breaks the manned capsule into a high Mars orbit. And the other Falcon launches the manned space capsule. And they both wind up in the same orbit, and they rendezvous with each other. Now, there's this interesting thing about the Mars Science Laboratory capsule design. That is, there's a little hatch right here at the top. And that hatch is used because before they launch, they don't want to have to put the RTG in there. It's producing a lot of heat. Thank you. I'm almost done anyway. So you can use that hatch to access the inside of the aeroshell to get to the landing capsule, get to the Savvy, and you can go along in that way. At that point, you separate the two spacecraft. You fire your propulsion stage to slow down for re-entry. You perform your re-entry, and then your sky crane system sets you down on the surface, and it's already done these with the ascent vehicles. At this point, it deploys. You have a couple of little robot arms. You go roving around on the surface for a few days. This design is nice because you don't have to get out of your rover to collect a sample. You don't have to contaminate the samples with your biology if you don't want to, but there's still the option. There's a hatch there that you can get out and you can wander around on the surface with. Well, at the end of this day, you go, you meet up with the two other ascent vehicles. They drop off most of their solar panels. You collapse your rover back down, you lie down in there, and the ships come together, and you need to be able to find a fairly smooth place to do this, so your site needs to be a good smooth area. But they attach like so, and then first and second stages ignite, so the first stage acts kind of as a strap-on. Alternately, you can produce more delta V by doing an actual staging event. You can see basically your rovers get vaporized in the process, but it'll get you back up to low Mars orbit. And then you drop the two ascent stages off, and that little box right there is a little capsule you're lying down in. And the propulsion module docks to your spacecraft. The mass for that is on the propulsion module. It takes you from that low Mars orbit you just reached up to the high Mars orbit, where you then transfer from your little Savvy over back into your manned capsule. And then that propulsion stage that just brought you back up there, you reattach to your manned capsule, you head back towards Earth, you perform a re-entry, you splash down in the ocean. So the architecture for doing this says, okay, we launch starting maybe 2016 as a potential. Your people are back on the surface of the planet by the end of 2020. It doesn't require any significantly new technology, at least nothing a person couldn't build in his or her garage. And you get, the honor of being the first person to land someone on Mars. So, are there any questions?
Using the Dragon capsule.
Yeah.
And they're using a different heat shield material than the Orion.
Mm-hmm. They're using the Pika X material.
Right. Now, is that, you need a different change in velocity to go from LEO to
That's right.
in from, is that heat shield going to be?
Yeah, that's one of the reasons I went with it. Elon Musk has said, we can bring this thing back from the moon or even Mars. It's designed for that from the very start.
So I know they got that design from NASA. They basically picked up old NASA. Why did NASA use a different material for Orion then?
I'm not sure. I understand they were trying to copy a lot of the materials used in the old Apollo program for that capsule, and they couldn't actually do it exactly the same way. Too much institutional knowledge had been lost, so they had to work out new processes. But, yeah. Yes?
I actually have two questions.
Okay.
In the beginning of this, did you ever consider in-orbit, Earth orbit, orbital refueling?
Yeah, absolutely. And I, like I said, I support that. If it's available, by all means use it, because then you can do it with maybe, just one or two launches. And it actually simplifies things a lot if you have the depot available.
The other thing I wondered is, aero brakes getting to Mars, Had you ever considered a hybrid system? I heard somebody else talk about this recently. You do aero braking, but it's designed not to get you all the way into the atmosphere.
Okay.
And then you use a chemical.
I've actually got an alternate version of this plan in which instead of the capsule going to low Mars orbit and then up to high Mars orbit, you just brake enough to get into not be at escape velocity, and then you can spend a few months aero braking, lowering your orbit in the main capsule. I just wanted to present something coherent rather than being all over the place. But
I just wondered if you
yeah, absolutely. Yeah.
What's the travel time from Earth to Mars?
That is right up here in this. Yeah, I got to go up a ways. That chart I showed you from the NASA interplanetary mission reference. You can return, counting the astronaut, if you discount the astronaut and his spacesuit, you can lift about 15 kilograms of samples up from the surface. All right, travel time. Outbound flight is 180 days. This is the value I used right here, this piloted value. You stay in orbit or on the surface for a total of 586 days. Your return time is about 180 days, so about 946 days would be your total using these particular values. Okay.
So you're still doing similar to Mars Direct, you're just spending a lot less time on the surface.
Right.
Total mission time is similar.
Right. Mm-hmm.
By the way, we are at 3:30, but
Okay.
if you're willing to stay, there's nothing after this till 6 anyway, so.
Okay, if there are any more questions.
You get a chance to get a copy of this presentation?
Yeah, if you want one, I'll give, yeah, sure. Get your email address, or if you have a jump drive, I can give it to you right, well, that'd be hard on this computer. I can email it to you. Yeah, sure. Okay. Sure. Okay, thank you.
Yeah, thank you.
All right. Yeah, you bet. Okay.
You were saying the shielding for the solar thing would be like 17
Grams per square centimeter.
That's for like solar. What about for like something, you know, cosmic?
Well, as Robert Zubrin says, you take the dose.
Okay. Okay.
You know,
There was some. I thought water. You know, like you're saying, a certain degree of water.
Mhm.
Well, I guess you'd have to have, what do they say, 33 feet is the equivalent of water to your
yeah,
atmosphere.
that's. I mean, if you want to do that, you can do it electromagnetically,
Oh,
and that's the
cool.
way they'll eventually do it, in my opinion.
Yeah.
But like I said, that's new technology we don't quite have yet.
That's
So.
cool. Electromagnetic. All right. Thank
All
you.
right, you bet. Just have to. How do I close this down without having to close it down?
I meant to bring some business cards, but I didn't, so I'm going to give you a piece of junk.
Okay, that's fine.
Hard for me either. If you could email me. This would be great.
Okay.
Thank you.
Yeah, you bet.
My dad, our family business is a Centaur rocket.
Oh, sweet. There you go.
Yeah, my dad designed the engines. My
Okay.
uncle was launch directors.
Mhm. Okay, you'll probably won't get these before Monday because that's the next time I'm going to have access to a computer, really. But okay.
These would be great. Because I think
Yeah.
that's going to be the vehicle.
And I agree. I just didn't want to have to put anything in the way
I
that.
understand. I have some doubts with Mayfield. I really don't know how to fuel. This is going to be an interesting problem.
I think ULA is convinced they can do it. You know, they.
There's technical problem. I mean, I'd like to see it, but
Yeah.
I do have some doubts.
What's
in
the
realistic
launch schedule
time.
now for the Mars Science Lab?
They're going to launch it next year.
Is it going to be nuclear powered?
It'll use an RTG.
Yeah.
Yeah.
A lot of advantages to that, though, wouldn't you say?
Yeah, I mean, continuous power availability
It's
and.
probably a pretty heavy unit, though. Weight-wise.
Wait, yeah, I mean, I think you get 3.5 watts per kilogram. It's under 30 kilogram unit, and it produces, or 36 kilogram unit that produces 130 watts.
If it does as well as the current rovers and lasts so
I'm trying-
much
yeah,
longer,
thanks.
it'll be traveling on Mars for years.
Yeah.
Let's hope it makes it.
Yeah, hope it land. I mean, the Sky Crane system, it's amazing how much you have to go through just to land that much.
Is that-
Do you think that's gonna be viable for Skytrain? I mean, it does seem sort of complicated.